This is IAT806 lecture 11.3, where we're continuing our algorithm segment. Now we're going to talk about Quicksort. You'd already seen that in sorting out sorting, but I'd like to show a little bit more detail in this lecture segment. As the name implies, Quicksort is the fastest known sorting algorithm in practice for general purpose use. There may be some special sorting situations and algorithms that take advantage of that special situation, but for general use, Quicksort is practically the fastest that's out there. Its average running time is, once again, here's that big O notation, is n times the logarithm of n. So n being the number of items times the logarithm of the number of items. So it's very fast. So that's a multiple of those two factors, by the way. So it's certainly better than n squared, but not as good as, say, n, which will be a single iteration through the list. So the idea of Quicksort is as follows. If the number of elements, first, here are some steps, and if the number of elements to be sorted is 0 or 1, then return, because there's nothing to sort. You got a single item or no items. Otherwise, you can tell that this is kind of a recursive algorithm that's going on. Pick any element, v, that's called the pivot, okay? And then partition the other elements in the list into two distinct sets. The S1, that's the set of elements less than the pivot value, and S2 is the set of elements greater than the pivot value. Okay? So take a pivot, take all the items throughout the list, put it into two chunks, the set that's less than the pivot value and the set that's greater than the pivot value, and then run Quicksort on those two sublists. So you can see this is a recursive algorithm, and the stopping condition, the base case, is you've run Quicksort on a list that has 1 element or 0 elements, just to take care of silly situations. So let's talk about what that means in a little bit more detail. So here is an example. We have an unsorted list here, 5, 1, 4, 2, 10, 3, 9, 15, 12. What I'm going to do is pick any element as a pivot. We'll take 10 as the pivot, and then we'll take all the elements in the list that are less than 10, put them in one side, and take all the elements that are greater than 10, put them to the other side. So 15 and 12 are greater than 10, and 5, 1, 4, 2, 3, 9 are less than 10. We then sort those things, and then we put them together. So you can see the advantage here, or at least how it works. The pivot ends up being the thing that you say is in the middle, because what you do is you take the entire list without 10 in it, and you put all the stuff to the left of 10 that's less than 10, and to the right of 10 that's greater than 10, and then you stick 10 in the remaining spot. And then you end up with some smaller lists that are also unsorted. You then run Quicksort on each of those smaller lists. Now, all of this is really typically taking place in an array in which you're moving stuff around. So let's show what that looks like in some more detail. So what we're going to do is, once again, take 10 as the pivot and pick that middle element, 10. We're then going to move that element to the start of the list just to get it out of the way. And we'll take what was at the start of the list, the 5, right? And we're going to move that, to where the 10 was. That's just initialization. The next thing we're going to do is we're going to create a first and last index pointing at the first and the last element of the list that you got, right? And what we're going to do is we're going to move first ahead until it finds 8 elements that are greater than 10. So first is actually pointing at 11, so that's greater than 10. And this last element, we're going to move it in the opposite direction until we find items that are less than 10. Okay? So first is located in the right spot immediately after where the pivot was. And then we're going to look at 12. It's not less than 10. 15 is greater than 10. But 9 is less than 10. So what we're going to do now is swap 11 and 9. So we're going to go on to a new slide. So that's a state, just exactly the same state we had before. We motored first from the starting position right here, and it found it was greater than the pivot, greater than 10. We moved last from here to here to here because this is the first element going in this direction from right to left, where the element is less than 10. We then swap those two. So 11 moves down to here, and 9 moves down to there. And then we move continue scanning and move first to the next element and check if it is greater than 10. And move it ahead, find if this is greater than 10. So 25 is greater than 10, so we're going to leave first there. And we're going to scan in the opposite direction for blast. That 3 is less than 10, so we're going to swap 25 and 3. And you can see there 25 went there, and 3 went there. We then move first to the next position and last to the next position. And they're both pointing at the same thing. And then we have a decision to make. Because they're both pointing at the same thing, this is the concluding segment, and we have one of two things to do. One is if this thing is less than 10, we just simply swap it with 10. In any case, what we're going to end up doing is swapping this with the pivot. And so 10 is now in the right spot, 9, 4, 3 are all less than 10, 25, 11, 5, 25, 11, 15, and 12 are greater than 10. And so we've successfully partitioned. Now the partition is nice and even in this case. It doesn't always happen that way in practice, but that's kind of what we ended up with. So that's the idea of how to partition. The next thing we do is call Quicksort on this thing and call Quicksort on this thing. So that's essentially how Quicksort works. So the procedure essentially is a recursive procedure. You call Quicksort with an array as an argument, and I haven't given you any sort of type details here, and left and right. And you need that left and right because you're going to recursively call it with smaller, narrowing down ranges of left and right. And so if right is greater than left, that is to say, if they're kind of, right is near the end of the list and left is nearer the beginning of the list, select a pivot index somewhere, doesn't matter where. You set the pivot index new to be the partition. Now we just showed what the partition was like, where you give it the array, the left and right, the pivot index that you picked. And what it does is returns, partitions the array, puts things in the order, and pivot index new, its purpose is to say this is where the pivot ended up, so that now you can call Quicksort on array left pivot index new -1, and then call Quicksort array pivot index new +1 to the right. And so that partitions, this calls it, recursively calls it on the left segment that you just finished partitioning, this calls it on the right segment. And that keeps recurring down until you've got 0 or 1 elements. I haven't shown the base case here of 0 or 1 element saying return right away, other than if right is greater than left. That's really the base case, but it's not really very explicit about that. It's implied by the condition of where the pointers are pointing at. So I've talked at some length about how these algorithms work. Part of the reason why I'm doing that is to help give you an idea, a flavor of how algorithms that solve, problems that we all need to, computing problems that we need solved every day, how they work, to give you a little bit of an indication of algorithmic approaches that you can take. And this one, and binary search are both examples of a general approach called divide and conquer. Take the problem, divide it into subproblems and sub-subproblems. The thing that's really important about this is that Quicksort is a very clever way of recognizing that you can cut the sorting problem into halves. And you saw a number of other clever algorithms in the sorting out sorting video. However, in Java, there is a piece of code that will do sorting for you. you need to set things up right for it to work properly. First, there's a method called sort that takes int arrays or float arrays, and it'll just put them in order. And behind the scenes, what it's doing is running Quicksort. Another variation on this, and we'll talk about how this functions later on in the course, is you can call sort with an array of objects. Okay, so just like calling array with an array list or something like that. So this is an array of objects, okay, not an array list. And you give it another thing called a comparator. And what the comparator does is a special class whose job it is to take a pair of items of the type that you passed that's in that array and yield 3 values on the basis of giving it 2 elements out of that array. So it's a kind of a tricky technique, and basically what it says, you not only pass in the array, you also pass in the means by which you compare elements in the array. So that comparator object, what that does is it's able to compare sensibly things in the array. So presumably this could, if it's an array of numbers, you don't need to do anything special. But if it's, let's say, an array of data structures whose job it is to be customer records, you can sort your customer records if they are stored in an array, because the comparator object knows the internal details of what is in a customer record and what less than and greater than means in the context there. So what that means is the details of how to do sorting you don't need to worry about. All you need to do is to provide information as to how to compare it. Now it sounds like a kind of an arcane technique, but it's very powerful. And we'll talk a little bit about how to do that later on in the term. There's also a binary search algorithm available. It runs on ints and floats, and once again, it'll do binary search on objects, just like the sort algorithm in the middle bullet there, just like this one here, where it will do, it will search for objects, again, using the comparator, the same technology essentially, and it needs this to be able to evaluate less than, greater than, or equal to. Obviously you need equal to, because if you're searching something, you need to know whether it's equal. Okay, so that's it for Quicksort with a little bit of Java stuff at the end, and that's it for lecture 11.3.